everyone. In today's review session, we will be going over LSTMs, specifically for time series. So as we know, time series prediction problems are a difficult type of predictive modeling problems. The complexity of sequence dependence is involved in a time series. In the previous session, we learned how to develop a simple multi-layer perceptron for a univariate sequence. But multi-layer perceptrons have their own disadvantages. In multi-layer perceptrons, you will have to provide fixed number of inputs for producing fixed number of outputs. You will need to specify the temporal dependence upfront while designing the model. There is also a fixed mapping function between the inputs and outputs in these feed-forward neural networks that can pose a problem when a sequence of inputs is provided to the model. Now, a powerful type of neural network designed to handle sequence dependence is called a recurrent neural network. The LSTM, which stands for long short-term memory, is a recurrent neural network that is trained using backpropagation through time, and it overcomes the vanishing gradient problem. So whenever we do backpropagation in deep neural networks and in unrolled recurrent neural networks, the gradients that are calculated in order to update the weights of the network can become unstable. So they can either be very large numbers or very small numbers. So when the numbers are very small, it can lead to a vanishing gradient problem. So LSTMs can have successfully overcome this disadvantages that recurrent neural networks specifically have, which is the vanishing gradient problem. Now, as you may see, this is a typical architecture of an LSTM unit. It has three gates: the input gate, the forget gate, and the output gate. The forget gate will conditionally decide what information is to be discarded from the unit. The input gate will decide which values from the input to update from the memory state. And the output gate will decide what to output based on the input and the memory of that unit. So as you may see here, we have the current input, which is xt, and we have the previous hidden state. These two are combined first. So I'll be referring to this as the combined vector. The combined vector is first passed through a sigmoid activation. This is basically the forget gate. And the sigmoid activation, as we know, squishes the values between 0 and 1. 0 meaning we forget it, 1 meaning we keep it. Then the combined vector is passed through a tanh. Tanh will squish the values between -1 and 1. This is used to regulate the network. And the same combined vector is passed through another sigmoid here, which will do a similar operation as before, which will squish the values between 0 and 1. Here in this case, 0 meaning it's not important, 1 meaning it's important. Now these two vectors are multiplied, the combined multiplied vector. Now this forget vector is multiplied with the previous cell state. And this process is a part of computing the new cell state. So whatever resultant vector we get here is added with the resultant vector we obtain after passing it through the input gate. Now the pointwise addition of these two vectors will result in the new cell state. Now in order to obtain the new hidden state, the combined vector is again passed through a sigmoid activation, which is multiplied with the vector that we obtain after passing the new cell state through a tanh activation. Now these two vectors are multiplied to obtain the new hidden state. So this is how a single LSTM unit functions. Now that we have a basic overview of LSTM, Let us now look at a simple example. Okay, so in this example, we are specifically looking at LSTMs for modeling univariate time series forecasting problems. Now, these are problems comprising of single series of observations, and a model is required to learn from the series of past observation to predict the next value in the sequence. In this example, we are looking at 5 different variations of LSTM. Let us first start off with the data preparation. So the data preparation is basically used to split a univariate sequence into samples based on a given time step. So the first architecture we are looking at is the vanilla LSTM. A vanilla LSTM is an LSTM model that has a single hidden layer of LSTM units and an output that can be used to make a prediction. So here is how we have used the LSTM layer here, followed by one single output that we are predicting. The next architecture that we are looking at is the stacked LSTM. So multiple hidden LSTM layers can be stacked one on top of another, which is referred to as the stacked LSTM. Now, an LSTM layer requires 3-dimensional output, and LSTMs by default will produce a 2-dimensional output as an interpretation from the end of the sequence. Now, we can address this by having the LSTM output us a value for each time step by using return sequences equal to true. And that is what we have done here. So here we have set return sequences equal to 2. And we have 2 LSTM layers stacked one on top of another. The next type of LSTM that we see in this example is a bi-directional Lstm. So in some sequence prediction problems, it can be useful to allow the LSTM models to learn input sequences both forwards and backwards and then concatenate these interpretations. And this is typically how a bidirectional LSTM works. Now we can implement bidirectional LSTM for univariate time series as follows, where we use the bidirectional wrapper on LSTM. And again, the rest of the architecture is very similar to what we have seen. The next architecture, next type of LSTM, in fact, here is a CNN LSTM. We know that CNNs can be very effective for extracting and learning features from one-dimensional sequential data. And here specifically, we are using it for a univariate time series data. Now, CNN LSTM is basically a hybrid model with LSTM backend, where the CNN is used to interpret subsequences of input that together are provided as a sequence to the LSTM for interpreting. Now, this hybrid model is called a CNN LSTM. Here we use the time distributed layer. This wrapper will allow to apply a layer to every temporal slice of an input on top of a 1D convolution layer. The next type of LSTM is the Conv Lstm. This type of LSTM is related to CNN LSTMs, where the convolutional reading of input is built directly into each LSTM unit. Now, this can be used for reading two-dimensional spatial temporal data, but it can also be used for univariate time series forecasting. And here we use the Conv Lstm 2D layer. Okay, that's the end of this tutorial on LSTMs. Here I have posted a list of useful resources that I have found helpful while preparing this notebook. Please make sure to go through these for a better understanding of LSTMs.